Ah, there we go. Hey folks. Oops. Yeah. I do have the YouTube chat open if anybody has questions or whatever. I haven't done a live stream in a very long time. Hmm. Be right back. My resolution is wrong. Alright. Apparently this is the non-optimal video resolution, but they won't tell me what the right video resolution is. Anyway. So, spend some time going through this checklist. This is a checklist that Andrew Sonnenberg has up on GitHub, and pretty comprehensive and useful. I've been using it for a couple designs and definitely caught some issues. So this connector is actually just going to be some pins or some holes on the board, so I'm not too worried about the pin out for that. Caps and things I'm not particularly concerned about. I made this symbol, but we should probably go check anyway. I put a link to the data sheet. live from you. Well, you know what? I should add a resistor on that so that I can actually remotely trigger that if I need to. Any other pull-ups? Like I said, I do have the chat open. Happy to answer questions. If you just want to watch it along, fine too. The basic flow of this device is have a USB header up here at the top and do some filtering on the V bus coming in. And this is actually an Esd protection package from ST. So what's really nifty about that is it's this entire Esd diode setup so that it actually handles the pinout actually runs straight through, so your I/O lines have minimal impact, and it's designed for USB, but it also clamps your V bus and ground, so you get Esd protection across all the inputs from USB and in one nice chip that is layout friendly. So that's just coming into an FTDI FT234XD, which is a slightly reduced pin chip. Where FT232s are really common, this is a slightly less expensive chip if you only want to do serial. And there is an FT230XD, which has more CBus lines and the full breakout for all the serial. I just happen to already have 234 XDs, and I was trying to fit this into a small package. So down here we have a analog devices isolator. So it's with this particular cable, it's actually designed to connect to an ECU. an aftermarket ECU, and my original design did not do isolation, and so I didn't actually bring in the 5-volt, but I did tie the grounds together, and I found a lot of issues with if the car was turned on when the USB cable was plugged in, or various situations that the USB or the FTDI chip in that case, which was a 232R, would actually just lock up and do all sorts of odd things. So I'm putting in this full isolation to hopefully deal with some of those issues and make it so that a little bit more tolerant of bad behavior. For example, it's not uncommon in cars to really screw something up and have a big surge come in on one of your input pins. So here on the ECU side, which will be a DE9, the VCC, or the 5-volt input from it, comes in, and we've got some reverse voltage protection, a little bit of current limiting and filtering, as well as a diode clamping it. And that, along with these series resistors and another one of those ST ESD chips, means that you should be able to put 10, 15, maybe even 20 volts on any of these pins, and it will clamp it down in internally. This will shunt the ESD chip will shunt power from these IOs or from VBus or into VBus, and in this case VECU, and that will eventually end up back at this Zener, which is rated to take most of that. And then of course this has the isolation barrier, so we shouldn't have any bleed through across. The only other really odd thing on this design is I'm working with I'm making the cable work for an even older ECU than the one I initially was designing for, and that one, most of the pinout is the same, but they requires an additional pin, which is actually just a clock signal. It's like 16 times the baud rate, as you're providing it the serial baud clock and baud rate clock. So this is not exactly what the manufacturers put out eventually as their schematic for it, but this is a part, this NJU part is something that part that I actually heard about from Eric Schleifer from Tube Time. He was using this for something else. And it's a nice little part if you need something that takes a crystal and has the oscillator as well as some of an initial divide down, a convenient one-chip solution. And I tried to do appropriate guesses for getting the crystal selection correct to meet with this particular chip. It has some built-in capacitors for the load, and walk through that again. So internally, this is just a Pierce oscillator with a counter that has taps off of it. And so they don't actually provide enough detail to properly calculate what the load should be, or all the different things like the transconductance for your critical transconductance and everything to make sure that this oscillator will actually start. So what I've done instead is I started with that the chip internally, you can see here, has CG and CD. And if I come down and look at what CG, CD actually are, it says that it has internal capacitors that when you run at 16 megahertz should be 15 picofarads on either side, for CG and CD. And so starting with my crystal parameters, this crystal is 150 ohm ESR, 7 picofarad shunt shunt capacitance, 20 picofarad load capacitance, and a nominal drive level of 0.1 milliwatt. So I was making some rough guesses about what the capability was for transconductance, or what the maximum transconductance that this chip can actually offer in terms of its drive capabilities. And so these are guesses, because they don't actually give me a GM crit or a GM to match. So I'm just assuming that it's a CMOS output from this NAND gate for the XT bar, and in that case, if I take the input current required to drive this input in the NAND gate, and the output high voltage, so the minimum voltage, then this is a rough guess of how many milliamps per volt I actually need in terms of the transconductance. Calculating load capacitors is slightly trickier. Well, actually, calculating GM is really tricky. And then trying to calculate power. This is actually an older version that while I was still trying to understand how to calculate all these things. So there's a good chance that this is just the power ratings are wrong. So I'm ultimately going to set this to 0. What I've found from a lot of reading is that there's no good way to actually calculate drive level. Pretty much everything says, here's how you calculate it once you measure in system. So by putting a 0 ohm resistor on the drive side of the crystal, there are a couple techniques for measuring that will let me reverse calculate that and come back to the actual. And so we can change that later if we need. But this is the RX initial is a generic, if you're trying to pick an initial crystal value or a initial series resistance for a crystal, you can set it equal to the reactance of this capacitor, and essentially think of this as the drive voltage coming out through a resistor divider, where this side, the low side, is actually of the divider is the reactance of this capacitor. So you'd end up with about half the voltage here, and so that the recommendation is you actually put in an 820 ohm potentiometer, and then you turn that down to find where an acceptable startup still works. Because often, if you run a value like this through and calculate your transconductance, you'll find that if you cut your power in half, that you have now gotten way below the GM crit. But in our case, we don't actually know what GM crit is, so it's hard to say. So I'm actually just going to take out some of these notes because they're wrong and misleading. And misleading notes in your schematic will confuse everyone. Now this says CL1 and equals CL2 equal 40, and so that, but I have 25 here, so there's a good chance that I did not finish running that calculation. So let me go borrow. It's actually a spreadsheet that I put together for work because I kept running into crystal calculations. So this actually follows from primarily from ST. ST has an app note. I can find the app note. So ST has app note AN2867, which is oscillator design for the ST32 microcontrollers, and it just has a lot of good theory, as well as how to run most of these calculations to figure out how the oscillator is going to behave in a Pierce oscillator and how to calculate the various critical parameters. Like I said, in this particular case, I can't do a lot because the datasheet simply doesn't, for the oscillator in this case, doesn't tell me enough. So I can fill in a few of these values and say, if I assume pin capacitance, which unfortunately, again, I don't think I get a pin capacitance value. They're just repeating this for different VDDs. So in my case, if at a VDD of 3.5, this is irrelevant. 9. Yeah, they don't really say. So I'm gonna assume 5 picofarad of pin capacitance. And so this is running some calculations, assuming that you want 2 equal load capacitors to balance it out. Now in my case, in this case, we have a calculation spits out that, hey, I actually want 35 picofarads when I do this. But remember that in here, I have 2 internal capacitors that are going to be around 15 picofarads. So I need to actually size these appropriately, that I'm not going to have, or I need to account for the 15 picofarads when on the internal pins. So yeah, if I do that, like I said, the transconductance numbers are going to be completely wrong because this is the actual GM crit that is calculated here should be correct, but I don't know. I don't have anything to compare against. The GM crit max, I don't know. So in this case, the transconductance is quite low. Should work. Probably going to end up with way too much drive power, and so I'll have to come in and tune the resistor later. But if I have 35 picofarad here, let's change my note. Right, I already put my note of having internal. So these then need to be 20 picofarad. And back to validating footprints. Okay, so I'm doing the TDSP. Oh, right. Set for how to make this little table. I really wish KiCad had a way to make a table. And so now it's very obvious that I'm making this be FO divided by 32, which in my case, 9152, 49152, 00. And if I divide that by 32, I get 153,600, which if I divide by 16 is 9600. So this is a 16x the 9600 baud, the actual design target. So that pinout is verified. Don't need to validate these. These quad isolators are pretty neat. They they come in a variety of configurations. So there's 4 in one direction, there's a 3 with a 1 return, and there's 2 and 2. And then also within these, there's the D or the E, which is whether you have disables or whether you have enables. And the behaviors are different. And then there's actually another suffix here, the 1, which sets what the default state is for the output pins when the disables are in play. So I've chosen this specifically here so that when the VDDI, so when the input voltage on one side is powered, and when the other side, is unpowered, then they are going to tri-state. And if the output is powered but the input is unpowered, then it will drive high on the output side. Basically, I don't care what the input is. It will just drive high until the input side is powered. Then if both are powered but I have a disable, it will also drive high. And since I'm doing a TTL serial, that seems to be, holding the signal high seems to be the right thing to do. This seems to be right. Mostly grabbed symbols out of the KiCad libraries where possible, but that means I need to check them all. And this is another, just a 4 I/O version of the same Esd protection on the USB side. We may have to shuffle these a little later when we start doing layout. Could be the corners. Okay. That seems like that's good. Checking that things match the package. I don't think these only come in one package. Oh, this one comes in 2. So they're the same pinout. We'll need to note which package we want. A little bit here. This only comes in a DFN. I think. Yeah, DFN. That'll be fun to solder. This one. Getting the EVSP10. Yep. All right, so good on that. Thermal pads. Now the only one that I know of that has a thermal pad, that's an SOT, that's an SOT. This is SOIC. It comes in SOIC narrow, SOIC wide, or QSOF. Oh, no thermal there. It's only this DFN. Which, if we check, they label pin 13, which is the center pad under the IC. Fair enough, that's what we have there. Okay. Don't have any debug interfaces on this. Alright, so this is one where this next one, power voltage tolerance ratings specified as required. I have gone back and forth a little bit on how to actually do this. So you'll see that a lot of these have 10 nanofarad and a 5.5 volt DC bias all in the value field, and I've actually come to decide that that's probably not the right way of doing this. So what I've started doing is putting in separate fields for things like DC bias, and so value ends up being just the raw, like intrinsic value of a component. So in this case, the capacitor is 10 nanofarads, but it also has a constraint of a 5.5 volt DC bias. And this is important for when I go to do component selection, because capacitors have a inherent, ceramic chip capacitors actually have a derating that occurs when you have a bias voltage on them. And so if you actually need 10 nanofarad at a 5.5 volt bias, you got to actually go check the data sheets and find out if that's actually, like, you may actually have to go to a considerably larger value, even though, because when you derate for that DC bias, it will actually be considerably smaller. So I'm not going to do that right now, but I do want to go through here and change some of these parts. So like, for example, this one I even put in a part number. But the thing that I'm actually interested in about on a EMI suppression filter, ferrite bead, I'm not inherently looking for that specific part, and while most of the time it's perfectly fine to just list that part, I'm interested in actually listing my constraints and then being able to resolve that later. So in this case, a BLM 18AG is actually 120 ohm. Well, actually, we'll have to go look at part number. So BL is chip ferrite bead. Type ferrite beads, single type. 3 is the layout, so an 063. 4, general use. 5, impedance, expressed by 3 figures. And this is the ohms at 100 megahertz. So the part that I've actually chosen here is first and second digits are significant, and the third expresses the number of zeros that follow the first two. So this is then going to be a 500 ohm at 100 megahertz. Now, like in this particular case, these caps are on USB lines, and they don't actually experience a DC offset, or at least they shouldn't. The line should be constantly active, but it's important to know what the peak-to-peak voltage is, because I will need to know that when I actually choose the voltage rating for the part. And on these where it's got a 5.5 volt bias, I'm just assuming that VBus from USB will actually float up to 5.5. It could be as low as 4.5. USB allows quite the range. And in this case, the ECU itself provides 5 volts. It's noisy. It's very noisy. All right. Pretty good. Here, where I've got to pull up, the power would be 3.3 volts across 10K. So nominally, this should be uh, 300 microwatt, or sorry, that's the current, and I need to times 3 power going through it. I want to make sure that it's extremely unlikely, but I want to make sure that I don't end up exceeding power limits on the chip capacitors, or chip resistors. So this being likely will be an 0603, and in that case, that's just sort of my default. And if I do that, then that should be a 10th watt. So it's good to validate and put in my constraint. So like here, if I were to assume that I had, I don't know, let's say 30 volts, not unheard of in a vehicle. If somehow I ended up with 30 volts on this line, I'm going to lose a little bit coming across this diode. Probably 0.7. Unless I shock here thing. So VF is 1 volt. So I'm going to lose about a volt. Actually, that's not good. Because if I'm getting 5 volts there. Yeah, see, that's actually not going to work for me. Instantaneous forward voltage. I actually want a very low VF for that. Because I'm going to come in with, this is, maybe we can label this. Really? This is going to be nominally 5 volts DC. But if I have a diode drop on the other side of this, it could be as low as, what, 4 volts. Now, would this chip actually work in that circumstance? Good question. If I go look at specifications, so we have 3.3 volts on both sides. Okay. What is allowed from a all of their test conditions list having the 2 voltages equal, and I am actually intentionally not doing that. So I'm assuming that that's not going to be an issue because it has, it has an isolation, so they shouldn't care. And so this chip should work all the way down to all the way down to 1.8. It's just its specifications will change a little bit. That's probably okay. But let's go back and let's just assume that this had no drop. And if I were to have 30 volts on this side and it goes through my ferrite and is being pulled, the Zener is going to then start drawing power through it upwards, or to try to constrain this side of the ferrite at 5.6 volts. So what would happen is I'd have 30 volts on one side, 5.6 on the other. So I'm going to have 24 volts between this side and this side, and it's between the ferrite and the resistor here. Let's assume that that's primarily going through the resistor. So if I have 24 volts and I'm going over 470 ohms, I'm going to pull 51 milliamps through this resistor, and then going back and multiplying that out, I'm going to pull 1.2 2 watts through. Let's say 1.3 watts. So there's a really good chance I won't be able to use that as an 0603 because it will just because like that's going to be way more than a 10th watt. I mean, if I put 30 volts through that the thing would melt right now. Now, similarly, looking at the Zener, how much power can it take? That's the SMAZ 5919B. Right, 5.6 volts. So it's supposed to have a maximum Zener current of 268. Total. Sure. So here we see it can take up to 1.5 watts, but only if I put large copper pads around it. Now, in this particular case, if I put 30 volts in, I'm gonna have gonna have a lot of power going through it, because it's actually gonna be current is gonna be consistent going through. Because it's going to have that voltage drop, which means that much current, that the 0.0519 in terms of amps, so 51 milliamp, which is well within the Zener current. So we can say I think that mostly takes care of all of them. I'll have to come back to capacitor derating a little bit later. Not expecting to need any polarized, but I'm going to leave that open for now. Okay, fusing and reverse voltage. So I did put reverse voltage in here. I'm not happy with this being a 1 volt drop though. I believe I picked that a long time ago because that's a very common 12 volt reverse protection diode. And I probably want to find something else for that. So go ahead and move that value for now. Now I didn't put reverse polarity protection on the USB side. I'm just going to assume that if I'm assembling this, that I won't make that mistake. In this case, it's good to check your input capacitance and inrush limiting. In this particular case, we have very little, and it's USB, so if I inrush too much, it's gonna cut me off. Don't really have a regulator, so under overvoltage isn't needed. We're not going to use power estimates. We don't have any current sense. Don't sense. We don't have any power rails, so decoupling for all ICs. Okay, so we got decoupling here. We got decoupling here. Technically bypass, not decoupling. Bypass here. Bypass. Yep. All those. Do I have a bulk at this side? I have a 10. Well, that's more of a filter. I want a bulk. And I have a 4.7 over here. And the VCC doesn't go to a whole lot. It actually comes off 3.3. Which does have a bulk. Okay. Power inputs. VCC, which is relic. 3.3. Okay. Right, so this is the high power discretes and passives. Make sure, and the worst case is going to be this when I put, I may not I'm going to have to think about that. How much do I care about the 30 volts? Like this, that would be a severe accident on this device. These would be the same, actually. They're all going to limit the current flowing back into the ECU via the ESD protection. But at 30, and the other way to do this would be to increase the resistance beyond 470. What I need. Well, that puts you pretty high. I want to resistor this mount to 1. Three to 1.5. $25.12. Big part. Deep. Now if I reran that and assumed I was only get up to 12 volts, because, you know, car, 12 volts. So 12 minus 5.6 from the Zener. I'm going to drop 6.4 volts over 470. 13 milliamps. Or 87 milliwatts. See, that fits. Yeah, alright. That makes a lot more sense. And that lets me stay in the 0603. So okay, log rails to care of. These should all be at the same logic level. These should be all at the logic level. That should be at that logic. Good. We don't have any open drain or PECL. No real high speed or gigabit. Do have a TX-RX pair, so that's why I drew little arrows, because it gets confusing otherwise. So the TX going out, RX coming back. I really hope I didn't screw this up, but I have gone back and verified against actual cables that I've made that work with this. And if I do screw it up, well, I'll fix it in another spin. No differential pairs. Active low signaling. That'd be reset, and I'm intentionally pulling that high. No banking rules. Okay. No time constants. Alright. Go up. Okay, oscillator is checked already, and along with the load caps. It does have an integrated crystal driver. I've already checked that. Pull-ups to define state. The only case is this one, which we validated here. And we want that to be low. That's correct. Don't have any circuit programming. Great. No power outputs. Do have ESD protection. You know, that's not a terrible idea to actually do this, although I know for a fact that this needs to be this frequency. It would stink if I have to rework it, but yeah, we'll just leave it alone. Okay, test points. So test points are handy, and we probably should dump a few in here. So some interesting test points. Not have that library. Oop. Why don't I? I know there's a library for this. I have used it. Test point. Oh no, that's the footprint. It should be in device. Oh, hey, you know what? I don't have device added for whatever reason. Oh, I do. Hmm. There we go. Okay. So, things that I probably want test points on. I am going to want to look at this crystal output. And pretty much always want to have a test point to ground. At least one. And in fact, I'm going to want an ECU ground as well. I usually like to put in voltage rails as test points. Because my goal is primarily to make sure that the device is starting up correctly. So, like I could make test points for the actual serial pins. On this side, they're actually directly on the connectors, so I don't need to worry about it, and same with the USB. So it might be nice to have these broken out. A non-ugly way of doing this. I think that's probably all I want. The test points are good. Ready. Okay, so now we should go back and actually do some component selection again. No matter how many times I do this, I always find out later that you end up with like 7 or 8 different part numbers. Because the manufacturer has a part number, but then so does the distributor, and so you just better off actually calling them MPN for the manufacturer part number and like EPN for the distributed part number. Okay. Over. Cool. So yeah, passives. I think passive. So I'm a fan of just picking a brand and going with it, following in that line. So in my case, I want So let's be X7R. And capacitance, let's start with a 10 nanofarad. Which is also 0.01 micro. Capacitors often will go from micro to pico. So if I go and pull up a data sheet for this, so here we get the breakdown of the actual part number. And so I'm going to want a C0603 with a C for the standard. I'll have to put in the capacitance and tolerance, and then the voltage rating, etc., etc., etc. And so that's why there's a 0603 C103 K, which is tolerance. And there's a 5 and a 1, and if we go back and look here, after the tolerance, there's 50 volt and 100 volt. And then the rest of it is the same, RACTU. And so the 5 probably is fine, the 50 volt, but remember what we want to go look at is what is the capacitance versus bias, because I know where did all my I have a CV bias. Oh, there we go. Oh, did I accidentally put R107? In P. Okay. So I want to group by that. I want to turn off that, group by that. Don't care about footprints so much at the moment. Okay. So if I look at this 10 nanofarad 0603, right, so I'm looking at the 0603 50 volt bias. So I'm only ever going to have 5.5 volts on this part, right? So C101 up here. And you might think, well, I can just go ahead and put like a 6 volt capacitor on it. But if I actually went and found a 6 volt rating in that size, I mean, I don't think there's gonna be okay. So this is we had to go to an 0402 to find something, but this has a 6.3 VDC, and we'd think, well, I'm only ever going to have 5.5 volts, so that'd be fine. But then if I look at this capacitance versus bias, if I come all the way out here and I'm biasing at 5.5 volts, I'm actually going to lose 0.5% of my capacitance just due to just due to that voltage, that bias voltage. So it depends on how critical things are. I mean, keep in mind you're already picking a 10% tolerant part, so is an additional 0.5% gonna make that big of a difference? Probably not. And but maybe it really depends on your scenario, and things can get worse in other parts. Now in this case, looking at the 0603 versions and a 50 volt, my bias, if I'm down here, again I'm losing about 0.7%, but also look, in the 50 volt rating, if I were biasing this at say 35 volts, which is well within its rating, right, it's okay to do that, I would still have 16% off, and that's in addition to the 10% tolerance already. So I could have been way, way, way off. Now in my particular case, it doesn't matter, right? Like I'm for a 10 nanofarad part, it's whatever. So I'll go ahead and put in this part number. I'm using Chemet. And I'm just going to go ahead and find the next one. I like to just keep things relatively consistent. If I put it in volt range, now I can go find my 100 nano. Wait. And so the 0603 104 K5 ETU, fine to me. Now, just to satisfy my curiosity, 5.5 volts, down 2.2%. Again, not too bad for this. But I'm gonna guess that as we look at bigger parts, like a 4.7 UF, okay, so now we run into a problem. I can't get a 50 volt 4.7 UF in an 0603. Can I get 4.7 UF in 0603 at all? No. And this is one of those things that is a gotcha sometimes when you're doing your design. So I can get it in other tempcos. I could get it in an X5R, but I don't want it in an X5R. In an X7R, because I like to be consistent. So I probably have to bump up to an 0805. And in fact, that's what we see here, that there's a lot in stock of an 0805. And as far as voltage ratings go, now if I tell it that I want a 50 volt, it actually tells me that for 50 volt, I probably have to go up to a 1206. But there's a chance I could do a 35 volt if it's reasonably common. And it looks like the answer is no. So I could get an X7R 0.5. Okay, so they have a 16 volt in an 0805. But if I go and look at my C over V, and I'm going to put it at 5.5 volt, I'm going to be 37% off in this case. And that's no way. So probably it makes sense to go ahead and bump that up to a 1206. And there's a lot of these in stock at 1206. And there's a lot of them at a 50 volt part. So we're going to go ahead and change this to a 1206. Add in. And this is part of why I wait to do these parts toward the end. Now here, the only difference between these capacitors that are 100 nanofarad and this one up here is that they're going to be biased at different voltages. Now, since I already know, since this is, the bias voltage up here is greater than the bias voltage here, I know that I can just reuse that part. I know it's going to work. Similarly, for the 10 nanofarad, I know that I can go grab this 10 nanofarad and it'll be fine. And this one here. So I need 47 picofarad. Now the fun thing when you get into picofarads, well, before we do that, let's go look at this 4.7 at a 5 volt. Now we have a 4.7 at 5.5 volt. So we kind of already know what's going to have to happen. It's going to be this one. And this is going to have to go up to a 1206. And then this 1 nano, don't have. We have a 47 pico, a 1 nano, and a 20 pico. So let's go look at this one nano. Picofarad. I should just get in the habit of writing it that way. For whatever reason, no one uses nanos. You go micro to pico. Well, actually, I know why. Because you used to have micro instead of pico. So this would be 10,000 goes. Picos. Actually, that's right. And that's where they switch. They don't say 10,000 pico. They say 0.01 micro. Okay, So anyway, 1000 picofarad, 0603, 50 volt. And then now I get into these odd ones. So clear all, and I'm going to do that because the tiny values in the picofarads. If I'm down here at, say, 47 picofarad in an 0603, there are very common parts, but they come in C0G. So there's a different temperature coefficient that happens at the very low end of the spectrum. So what is the difference between these ones that they have millions of? Okay, so they have 5% tolerant ones, show that has a lot more stock. So I just take that as somebody else is using this. No, in my case, the 47 picofarad is what? Oh, that's on my USB lines. So yeah, that's a good reason. And then here I've got my 20 pico. Okay. Should not be using the resistor pad for ferrite bead. Should be using probably an end. And as far as resistors go, I've got a couple of these that need certain power ratings. So everything should be under 10th watt. Stock. Those 27 ohm. CW 060 actual. Minute code. 27R0. J for tolerance, which is +5%. N for the TCR. Temp code 200 parts per million Kelvin. E, the packaging. $5,000. 10,000. Won't be building 10,000 of these anytime soon. Now I bet I can find CRCW 0603 and they do their code. NK0 JN. CRCW 0000. You know what's always fun is that you have to have a tolerance code or a jumper. Okay. So if I want to add a footprint for my test, so I just have a habit of making ground test points square and everything else circular. So the only things I'm missing is I need to go pick a new diode. Not happy with that forward voltage. So I put entirely 5. I get Schottky with, okay. Schottky diodes usually have these really, really low forward voltages, so that's why I went and picked that. I don't know why it was not. But now if I actually go pick some D. Now the other thing I need to recall is that I have current expected to pass through that about 52 milliamp. Minus 5.6 over the 470 volts. or 470 ohms, 13 milliamp. So forward current. $40 volt, 200 milliwatts, single direct. .28 volt. Nice. Mm. Higher than forward continue 30 milliamp. So the forward voltage in that case. Hmm. 523. I don't think I'm going to get to layout tonight. It's been a lot longer than I anticipated. So changing to the pin 0 here is the mounting pin and shield of a D9. And when I was using the generic connector, they didn't have a pin 0 to match the footprint, which has a pin 0. So switching over to using the DE9 symbol, they actually shuffled the pins, which is making this a little bit annoying. But that's okay. The main thing here is that this TXD needs to be on pin 5. And that's gonna make a mess. Unless I bring a whole bunch of stuff higher. Yep, I think that's where we're going to leave it tonight. Everything is filled out in the BOM. Well, I didn't fill out the D sub, but up again. Oh, somehow I didn't end up with the next para part. This point. Cool. So with that, I'm going to check off these last couple items because all the caps are figured out. Schematic is checked off. So thanks for tuning in.